I just want to do one demonstration, which won't take very long, of the project for today, which is 106. Now, suppose you want to crack a password and you have a hash value. Now, what I thought people did was they would just start like A, B, C, D, and then A, B, A, C, and try all those to get in. And you could do that. Then each hash value would be essentially random, and eventually you get in. But they don't do it that way. They do it this way, and I always wondered why. Suppose you start with this word and you calculate the hash. And then instead of starting with a different word, you hash the hash. So it's been hashed twice. And then you hash this again and again. Now, so again, they'll be effectively random, but what will happen is eventually you will hash one of these and you'll get a number you've seen before. That has to happen eventually because there's only so many hashes. Eventually, as soon as that happens, you'll have an endless loop here. You're back to this one, so hashing the end of the loop here. So this is why they call it the row method. This diagram looks like the Greek letter rho. And so this is a way to evaluate the quality of a hash function, and it's a method used to crack hashes. So, and what's interesting is, if you calculate the total number of possible hashes, the length of the tail is approximately square root of that, and the length of the circle is approximately square root of that. That's how it works out, which actually is just from the birthday paradox. You know, if you have, if I have a room full of 30 students, and they each have a birthday, January is just month and day. There's 365 possible birthdays. So if I have 30 students, you might think there's only one chance in 10 that they'll have two birthdays. And if I picked a birthday and wrote it on the board, there's only one chance in 10 that somebody would have that birthday. But the fact that two of them would match, you consider how many pairs of students there are. And there's approximately 30 squared pairs. Each 30 squared over 2 if you want to get picky. So that's the point here. That's why as soon as you've hashed enough hashes that you have up to the square root of the total number of hashes available, then you have the number of pairs of hashes is the square of that number. So that's why you'll only have to do this up to the square root of the number of possible hashes before you'll have a collision. The length of this will be a square root, and so will that. So we can calculate this. So the first thing we're going to do is calculate a hash here. Let me just shove this to the side so I can easily get to the other window here. All right, so let's all right, so I'll just put this in. I'm in immediate Python. So I import the hash library, and now I calculate using MD5 hash. I'm going to encode the word A. I'm going to encode it as ASCII, and then do a hash, and then turn it into a hex digest. So I get this hexadecimal hash, which is the MD5 hash of the letter A. Now, I might wonder if I did it right, so I can just go to an online MD5 generator, and it will show me that the right hash is 0CC1. So it's right, 0CC1. So that's, now I'm doing it right. Now, MD5 is 128 bits long, which is pretty good, and I'm going to make it shorter, so I'm going to add, I'm just going to truncate it to only 2 hexadecimal characters to make a simple hash function. This will give me just the last 2 characters of MD5. So I just get the 61 here. And the point is, now I can feed in any string, and I'll get a 2-character hash. There are only 256 possible hash values. So now I can iterate that. So I'll run this stuff, and I can do it in immediate mode in Python here. All right, so I start with A, and now for 50 times, I'm just going to, that's my hash. I'm going to re-encode the same hash over and over and over again. The new hash is the old hash hashed. So I'll get a 50 of them, and there they are. So now, what I can do to see how the pattern here, now there's 256 possible hashes. The square root of that is 8. So I expect the tails to only be about 8 long. So I should have enough here that they're going to duplicate. So if I just make the window smaller, there will come a time when I can visually spot the numbers lining up. I see a 1E there and a 1E. So if I can adjust the width of my window, there we are, 1E, 1E, 21, 21, 79, 79. I'm in the loop. So I can see, here's the tail going up to here, and this is the loop. And it'll loop around forever. So that's it. For such a simple thing, you can spot it. That's the row method. It took approximately 8, looks like a little longer than 8 here, and approximately 8 around the loop. That's it. Now, if I were to start from a different starting value, let's get out of this. Let's go up to here and say B. Okay, and now all right, then a second enter will run it. There we go. Now I started at B, and see, since I left my thing at the width, you can see it's yeah, it's, and see now the tail is really short, but the loop is about the same length. So yeah, that's what you'll get. All right, so that's, and so you can just do a few of these. Start it with password instead of A, and first repeated hash as the flag, and then you can try doing longer ones. With 3 characters, it's going to be longer, and you might be able to still do it with this technique I showed you, but if you go to a 32-bit hash, you're going to have to write some Python. You're going to have to save them all and check each time you calculate a new one to see if you've seen it before. So you'll have to do that in the code. You're not going to be able to do that on the screen with this, because it's going to be 2 to the 16, which is 16,000. The tail is going to be 16,000, and the loop is going to be 16,000. So you'll have to write a little code. Yeah. You might be able to do this with that resizing the screen trick, but probably you should just write a code, memorize them all, and see if they're back. Anyway, so you just play with that, and it gets you used to this row method of hashing, and this will come back later. We're going to see some attacks that use this technique.
Some sort of modular formula should do the trick, right?
What's that?
Some sort coding that implements the modular operation should do the work, right?
No, I don't. No, modulus would work if you knew exactly how long the tail was. Here, it's going to be random, like you see. So the only thing you can do is remember them all, and then look for them. And that's why, now there is a technique we'll talk about later. If you have a really big hash function, you can't remember them all. So what you do is, like Bitcoin, you only remember the ones that start with a lot of zeros. Because you don't really need to remember them all. See, if I remembered them all, then I would catch it right here. But if I only remembered like every 10th one, then I would just go around this circle a little bit until I found it.
So basically, when you showed us the hashes, the result of hashing the ASCII, etc.
Yeah, this here.
So basically, right, the loop. So the 1E and 1E.
Yeah, that's the tail.
Right.
And this is now the loop.
Oh. Now let's look at the loop. The loop starts with 1E, and the second loop, and the loop starts again with 1E.
Right. And after it hits the same number, it'll be Yeah.
Go back to the picture one second.
Yep. Okay.
The 1E and 1E.
Yep. So 1E is here. This is 1E and this is E.
H4 and H10. I'm not.
No, this is EE. E is the last one that doesn't repeat. This one is the first one in the loop is 1E. And you don't know it's a loop until you hit again. You'll detect it here is when you'll detect it. Now you see the same number again. But if you only remembered like every 3rd or 4th one, then you just hit it. You wouldn't take more than one more turn around to catch it. That's why you don't really have to remember them all. You can remember certain targeted ones, and they tend traditionally to choose a lot of zeros to make the targeted ones, and that's how they ended up using it in Bitcoin too. It's a traditional mathematical technique. If you want to choose only some of the hash values to remember, you remember the ones that start with all zeros. That's just a tradition. So we'll see this come back again. But right now, it's just you understand hash values a little better from doing this project. That's all the goal is.